For most of human history, Pluto was not a world. It was a dot, barely more than a faint, distant signal at the edge of our maps. Too far away to matter. If you had asked scientists to describe Pluto before 2015, many would have expected something simple: an ancient, frozen surface, scarred by impacts, changing so slowly that geology would feel like the wrong word. Then, on July 14, 2015, New Horizons arrived. In a single high-speed flyby, one chance, one narrow window, NASA finally saw Pluto up close for the first time. And the first images didn't just add detail. They overturned the entire mood of the place. A bright, heart-shaped region spread across the surface, Tombow Regio, bold enough to be visible from millions of miles away. Nearby, a vast, smooth basin of exotic ice looked startlingly young, with patterns that hinted at motion and renewal. Mountains rose where no one expected mountains to stand. And at Pluto's horizon, sunlight revealed a thin, layered haze, proof of an atmosphere with structure, chemistry, and behavior worth studying. Pluto wasn't a dead relic. It was a complex, active story, written in ice, in light, and in time. To understand why Pluto shocked us, you have to remember what knowing used to mean. For decades, Pluto lived at the limit of our instruments. Even with powerful telescopes, it was small, faint, and distant, more a measurement than a landscape. From Earth, we could track its orbit, estimate its size and reflectivity, and watch subtle changes in brightness as it rotated. We could study its spectrum and infer that its surface held ices like nitrogen, methane, and carbon monoxide. We could detect that it had an atmosphere, thin and seasonal, because starlight dimmed in a distinctive way when Pluto passed in front of a star. But we could not see terrain. We could not watch glaciers. We could not trace the shape of mountains or the geometry of plains. We were building a picture of a world without ever standing close enough to read the handwriting. So the expectations weren't wrong in the careless sense. They were cautious. They were the best stories you can tell from far away, when every pixel matters and every conclusion carries an asterisk. And the physics seem to lean towards simplicity. Pluto is small. It orbits far from the sun. Sunlight out there is weak, and temperatures are brutally low. A world like that should lose internal heat over billions of years. It should become quiet, its surface dominated by impacts and slow chemistry rather than active geology. That's the trap distance sets. It makes silence look inevitable. New Horizons was designed to break that trap. Not to refine a fuzzy dot, but to turn it into a real place. To replace decades of indirect clues with direct images, maps, and measurements. And once you do that, the question changes. It's no longer, what do we think Pluto is? It becomes, how could we have missed this much? New Horizons wasn't built for comfort. It was built for precision. On January 19, 2006, NASA launched a spacecraft on a trajectory that reads like a dare: travel billions of miles, arrive on the correct side of a moving target, and do it on a schedule measured in years, without the ability to stop and try again. In deep space, you don't steer the way you drive a car. You plan, you calculate, you commit, and then you watch your choices travel through darkness at extreme speed. Within hours of launch, New Horizons was already leaving the familiar neighborhood behind. Its departure speed was roughly 36,000 miles per hour, one of the fastest spacecraft launches ever achieved from Earth. That wasn't a flex. It was necessity. Pluto was too far away for a slow cruise. If this mission was going to happen within a human career, the spacecraft needed a head start. But even speed isn't enough. Over interplanetary distances, small errors become enormous misses. A tiny navigational drift today can turn into a 1,000-mile mistake years later. So the mission became a discipline of patience, carefully timed trajectory correction maneuvers, constant tracking, and a flight plan built around physics you cannot negotiate with. The next major step came on February 28, 2007, when New Horizons performed a gravity assist at Jupiter. This wasn't just a scenic flyby. It was a critical boost. Jupiter's gravity bent the spacecraft's path and increased its speed, effectively shortening the journey to Pluto. It was the kind of move that feels like science fiction, but it's pure celestial mechanics, using a planet's motion and gravity to trade geometry for velocity. And then the mission did something that sounds almost surreal. It went quiet. For most of the long cruise, New Horizons spent its time in hibernation. Not because the team lost interest, but because spaceflight is brutal on hardware. Systems degrade. Power is limited. Risk accumulates. So engineers placed the spacecraft into a low-activity mode, waking it periodically to check its health, upload updates, test instruments, and confirm that everything still worked the way it was supposed to. Think about that. A machine crossing the solar system while most of its systems sleep, kept alive by careful design and by a rhythm of brief awakenings. A heartbeat in the dark. This is where the sniper shot metaphor becomes real. A sniper doesn't keep firing until something hits. The entire outcome depends on one calm, exact chain of choices made long before the moment arrives. New Horizons had to survive the time in between. It had to hold its orientation, protect its instruments, preserve its power, maintain communication, and follow a path that would intersect Pluto's position on a single day in 2015, at the exact distance needed for imaging, spectroscopy, and atmospheric measurements. And the most unforgiving truth was always there, waiting at the end of the calendar. Pluto would not capture this spacecraft into orbit. New Horizons was moving too fast. There would be no second pass. No looping around for a better angle. No pause to admire the view. The spacecraft would rush through the Pluto system, gather what it could, and keep going. That is why this mission was so risky and so extraordinary. Not because it relied on luck, but because it relied on discipline over nearly a decade. Mathematics, engineering, and restraint. The triumph wasn't only reaching Pluto. It was arriving prepared, exactly on time, exactly on course, with a plan that could execute almost entirely on its own. Because at Pluto's distance, even a simple question, "Are you okay?" takes hours to travel. By the time New Horizons reached Pluto, the mission was no longer about distance. It was about timing. This was never an orbital mission. New Horizons had no way to slow down enough for Pluto to capture it. There would be no looping around for a second look. No, let's try that again. It was a flyby, one pass through a moving target, at high speed, with every observation scheduled to the minute. On July 14, 2015, the spacecraft reached closest approach, about 12,500 kilometers above Pluto's surface. That number sounds clinical until you picture what it means in practice. A spacecraft arriving after 9.5 years, crossing the Pluto system like a needle through fabric, with the most valuable seconds packed tightly around the moment of maximum proximity. And here is the part that makes deep space exploration feel almost unreal. During the encounter, Earth could not drive the spacecraft. Pluto was so far away that radio signals needed hours to travel one way. If something went wrong, the team couldn't send a quick command and watch the result. They had to trust what they had planned long in advance. New Horizons had to execute a complex sequence on its own, pointing and repointing, switching instruments, exposing images, scanning spectra, measuring particles, checking its orientation, while it raced past a world no human machine had ever visited. The spacecraft also had another constraint. It could not do everything at once. The high-gain antenna that sends data back to Earth can't be pointed at Earth and at Pluto simultaneously. During the flyby, New Horizons had to prioritize science. It recorded data to onboard storage, kept its focus on the target, and stayed silent in the way only deep space machines can be silent, working at full intensity while the people who built it could only wait. So the encounter became a kind of controlled suspense. In mission control, what you watch is not a live stream from Pluto. You watch time. You watch predicted milestones. You watch the clock pass through moments that were planned years earlier. Camera sequences, instrument scans, the tight choreography of turning and stabilizing, knowing that the spacecraft is doing it all alone. And then comes the most emotional moment of a flyby, the proof of survival. After New Horizons finished the most critical observations and began turning its antenna back toward Earth, the mission team waited for a simple confirmation that the spacecraft had made it through. Not the images. not the discoveries. First, the heartbeat, a signal that says the machine is still there, still intact, still following the plan. Only after that could the real reveal begin, because the data didn't arrive all at once. It arrived slowly, bit by bit, across the long thread of space between Pluto and home. That's the strange truth of planetary flybys. The most important day happens in near silence. The world changes, quietly, before you even see the evidence. When the first high-resolution images came in, Pluto stopped being a dot and became a world with a signature. A bright, heart-shaped region dominates the hemisphere New Horizons saw best, Tombaugh Regio. And inside its western lobe sits the feature that changed the tone of the entire mission, Sputnik Planitia. It looks almost too clean, too smooth, too new. In planetary geology, young doesn't mean recent in human terms. It means something deeper, a surface that has not been battered into oblivion by time. On airless or thin-air worlds, impacts accumulate like a record. If a region has very few craters, it usually means the surface has been resurfaced, renewed, replaced, or erased on timescales that are geologically recent. Sputnik Planitia is one of the strongest examples of that idea on Pluto. Up close, the plane is divided into vast polygonal cells, a pattern that looks almost like dried mud on Earth, except here it spans tens of kilometers. The best explanation is both simple and astonishing. The surface may be the visible top of a slowly moving sheet of nitrogen ice, overturning from below in a process called solid-state convection. Not liquid flow, more like a glacier behaving as a living material. Warmer, softer ice rises. Cooler ice sinks. Over and over. A frozen engine, operating in near darkness. That is the moment Pluto stops being dead. Because convection is motion, and motion means energy. And then New Horizons shows you the edges of the heart, where the landscape gets even more dramatic. Mountain ranges rise several kilometers high, and the material holding them up is not nitrogen or methane. Those ices are too soft. The mountains are built from water ice, and on Pluto, water ice plays the role rock plays on Earth. At Pluto's temperatures, H2O ice becomes rigid enough to form towering, jagged peaks. So you end up with a world that behaves like a layered system. Water ice as bedrock and mountains, hard, structural, load-bearing. Nitrogen and methane ices as mobile weather, flowing, glaciating, depositing, retreating. Pluto's heart isn't a symbol the universe drew for poetry. It's a geological billboard. It says, this surface has been active. It says, there are processes here that can erase scars. And the shock isn't only that Pluto is beautiful. The shock is that Pluto is working, quietly, slowly, but undeniably. If you want the strongest proof that Pluto isn't a frozen relic, don't look for one dramatic landmark. Look for processes, repeatable physics that can keep changing a landscape in the dark. Start with what Sputnik Planitia is made of. Pluto's heart is dominated by volatile ices, especially nitrogen ice, with contributions from methane and carbon monoxide ices. At Pluto's temperatures, those volatiles behave nothing like the rigid ice we picture on Earth. They can be soft enough to flow like glaciers, creep into basins, and reshape terrain over long time scales. Meanwhile, water ice is so cold and stiff out there that it functions like bedrock, mountain-grade material. That mismatch, soft volatile ice on top of hard water ice rock, is the first engine. Now look at the most iconic pattern inside Sputnik Planitia, those enormous polygonal cells. This isn't a decorative texture. It's a signature consistent with solid-state convection, not liquid boiling, but ice slowly overturning under its own weight. Imagine a lava lamp, except the lava is nitrogen ice moving at a pace you'd never see in real time. Warmer ice rises, spreads, cools, and sinks along cell boundaries. Over thousands to millions of years, that circulation can do something profound. It can erase craters and keep a plane looking geologically young. And that is the second engine, overturning. But Sputnik Planitia isn't only renewing itself from within. It's also a trap, an enormous basin where volatile ices can collect and persist. A deep lowland naturally favors deposition. As Pluto's climate shifts with season and orbital geometry, volatile ices can sublime into the atmosphere and recondense elsewhere, migrating like a planet-scale breath. Even with an atmosphere that's extremely thin by Earth standards, there's still enough exchange to move material over time. The result is a surface that doesn't just sit there. It cycles. That is the third engine, volatile transport, the slow relocation of nitrogen, methane, and carbon monoxide through sublimation and condensation. Now zoom to the edges, where the story becomes even more physical. In places around Sputnik Planitia, you see signs that nitrogen glaciers can interact with tougher chunks of water ice, carrying them like rafts. On Earth, we'd call those icebergs. On Pluto, the concept is stranger. Rigid water ice blocks embedded in a flowing sea of nitrogen ice. It's not poetic, it's mechanical. A softer material moves, a harder material gets transported. So when people say, Pluto is geologically active, it doesn't need to mean earthquakes and erupting lava. On Pluto, activity can mean ice mechanics powerful enough to build, erase, carry, and recycle landscapes. Then come the structures that look almost too bold for a small world. The large, mound-like features informally known as Wright Mons and Picard Mons. These are described as possible cryovolcanic candidates, and that wording matters. Possible means the shapes are consistent with cryovolcanism, not that the case is closed. If cryovolcanism is involved, it wouldn't be molten rock. It would be an eruption or extrusion of icy materials, potentially water-rich slurries or other mixtures, building up broad, high structures over time. Why is that such a big deal? Because cryovolcanism would imply that Pluto has, or had, a way to move material from depth to the surface, another path for resurfacing. It would be Pluto showing a different kind of plumbing, not just slow creep, but interior-to-surface delivery. Which brings us to the most careful, most consequential idea in the Pluto story, the hypothesis of a subsurface ocean. No one is claiming we have a direct photograph of liquid water under Pluto's crust. What scientists do have is a chain of reasoning that connects multiple observations: Sputnik Planitia's location, the physics of loading and reorientation, and how a planet responds internally to a massive basin filled with dense volatiles. One proposed explanation is that Pluto could maintain a layer of liquid water beneath an ice shell, helping the planet's interior respond in ways that match the observed configuration. If that feels counterintuitive, liquid water that far from the sun, remember the key point: oceans inside icy worlds aren't powered by sunlight. They are powered by internal heat and chemistry, and insulated by ice. On a world like Pluto, even modest heat, combined with insulating layers and the right composition, can extend the lifetime of internal liquids far longer than your instincts would guess. And here's the emotional pivot of this entire block. Pluto doesn't need to be warm to be alive with change. It just needs to have the right materials in the right places and enough energy, however faint, to keep them moving. So when you watch Sputnik Planitia, don't treat it as a postcard. Treat it as a machine. A cold machine, operating slowly, but relentlessly, turning ice into motion, motion into renewal, and renewal into a surface that refuses to stay old. Pluto didn't just surprise us because it looked alive. It surprised us because it isn't alone. What New Horizons revealed is not a single dwarf planet with a small moon. It's closer to a paired system. Two bodies locked together so tightly that they orbit a shared center of mass in space. In fact, the Pluto-Charon barycenter lies outside Pluto itself, which is why scientists often describe them as a kind of binary world. Pluto and Charon don't behave like a planet and a typical moon. They behave like partners. And when New Horizons turned its cameras toward Charon, the mission uncovered a second shock. This moon has its own geological story, written in fractures, canyons, and a dramatic polar stain that looks like a bruise on ice. One of the most recognizable features is a dark region near Charon's north pole called Mordor Macula. It stands out immediately, a broad, reddish-dark cap contrasting with brighter surrounding terrain. The best supported explanation points to surface chemistry driven by sunlight and cold trapping, Volatile molecules escaping from Pluto can be captured by Charon's gravity, migrate toward cold regions near the pole, and then get chemically altered by radiation into darker, more complex residues. It's not a painted mark. It's a record of exchange between two worlds. But Charon's real drama isn't only color. It's shape. Across Charon's surface, New Horizons saw an enormous network of fractures and chasms, features that look like the crust has been pulled apart on a planetary scale. The most famous canyon system is Serenity Chasma, a long, deep fracture belt that suggests extension, not compression. In plain terms, the moon's outer shell appears to have been stretched. That kind of global stretching has a powerful implication. One leading interpretation is that Charon's interior may have changed volume over time, possibly expanding as internal water froze, or as the structure evolved in ways that forced the crust to crack rather than wrinkle. The key point isn't a single mechanism. The key point is what the surface is saying. Charon did not spend its entire history as an inert, unchanging ice ball. It experienced internal evolution strong enough to fracture a world. Then there's the stark contrast between terrains. New Horizons imaged regions that look older and heavily cratered, alongside smoother plains that appear to have been resurfaced more recently in geological terms. On an icy body, resurfacing doesn't need molten rock. It can involve icy materials flowing, relaxing, or being emplaced in different ways. Scientists have discussed the possibility that parts of Charon's smoother plains could be consistent with cryovolcanic resurfacing in the distant past. Again, not as a cinematic eruption, but as cold, slow planetary plumbing, water-rich mixtures, slurries, or softened ices reshaping the surface and then freezing in place. So by the time you've looked at both worlds, the big picture lands. Pluto is dynamic, with flowing volatile ices, cellular convection, and an atmosphere that glows at the edge. Charon is scarred in a way that suggests internal change, massive fractures, canyon systems, and surface chemistry that records interaction with Pluto. Together, they form a system that feels less like a lonely dwarf planet at the edge of the sun, and more like a miniature planetary laboratory. Two bodies, exchanging material, evolving differently, and preserving their histories in ice. And that's the deeper meaning of the New Horizons encounter. It didn't just give us a better Pluto. It gave us a pair of worlds, and a reminder that the outer solar system is not empty. It's complicated, it's active, and it still knows how to surprise us. New Horizons didn't just send pictures. It carried Pluto home in slow motion. On flyby day, the spacecraft did what deep space probes are built to do. It collected far more than it could possibly transmit in real time. At Pluto's distance, the radio link is thin and precious. Signals take hours to cross the gap, and the spacecraft has to share NASA's deep space network with other missions. So New Horizons stored the encounter on its onboard recorders, prioritized a small set of early highlights, and then began the long, patient work of returning the rest, bit by bit. That return wasn't cinematic. It was disciplined. The typical downlink rate after Pluto was only about 1 to 4 kilobits per second, a reminder that interplanetary internet is still mostly physics, not wishful thinking. Every packet had to survive billions of miles of space, arrive intact, and be verified before the next one mattered. And yet, that slow drip is exactly why Pluto kept changing in our minds long after the flyby was over. Because the story didn't land on Earth in one dramatic dump. It arrived like a careful archive being unsealed. Over roughly 15 months, more than 50 gigabits of Pluto system data made the journey home. The final pieces reached mission operations on October 25, 2016, downlinked through the Deep Space Network Station in Canberra, Australia. So when people ask, did we finish Pluto in 2015? The honest answer is number 2015 was the moment we opened the door. The months that followed were the sound of a distant spacecraft quietly sliding evidence across a table. Images, spectra, measurements, each one another reason our old Pluto had to die, so the real one could take its place. Pluto wasn't the finish line. After the 2015 flyby, New Horizons kept going deeper into the Kuiper Belt, where sunlight is weak, temperatures are brutal, and many objects have stayed almost unchanged since the solar system was born. On January 1, 2019, New Horizons raced past a small Kuiper Belt object now known as Arrokoth, the most distant world ever explored up close. And what it revealed is exactly why scientists call it a primordial relic. Arrokoth isn't a shattered rock. It isn't a scarred survivor of violent collisions. It's a contact binary, two lobes gently joined together, like a cosmic snowman made from ancient building blocks. That shape matters because it suggests a calmer kind of planetary construction. Instead of everything forming through constant high-speed smash-ups, some early objects may have grown through slow, gentle assembly, preserving their original structure. That makes Arrokoth more than a weird-shaped object. It's a clue to how the first planetesimals formed, those seed bodies that later built the planets. If you want to understand how a solar system turns dust into worlds, you study the places where time runs slow. The cold, classical Kuiper Belt is one of those places, and Arrokoth may be one of its purest witnesses. So this is the real twist. New Horizons didn't just show us Pluto was active. It also gave us something even rarer, a close look at a body that seems to have avoided most of the solar system's chaos. A small world that survived almost untouched, carrying the early blueprint of planetary formation, billions of miles from home. For decades, Pluto lived in our minds as a category more than a world. Distant, dim, and probably simple. And that, more than any equation, was the real error. Because New Horizons didn't just correct a measurement. It rewrote a story. Here are the 5 truths we can say without exaggeration. 5 conclusions that hold up even as the details keep evolving. First, Pluto is not uniform. It's a planet-sized collage of regions that look and behave differently: bright plains, dark ancient terrains, rugged mountains, fractured ground. It does not read as one frozen face. Second, Pluto shows signs of recent or ongoing surface activity. Not in the sense of fire and lava, but in the language of icy worlds. Surfaces that appear young in places, patterns that imply motion, landscapes that look renewed rather than simply battered and old. Third, the ices are geology, not decoration. On Pluto, nitrogen, methane, and carbon monoxide ices don't just sit there. They flow, they organize, they respond to energy and gravity. They shape terrain the way rock does on warmer planets. Only here, the bedrock is water ice and the weather is frost and vapor. Fourth, the atmosphere and haze are real and scientifically crucial. Pluto has a thin atmosphere and it has layered haze that was directly observed. That means chemistry is active in the sky, and the surface and atmosphere are connected by a cycle of freezing and sublimation over seasons. And fifth, one flyby changed how we think about an entire class of distant worlds. Pluto is not an exception you can dismiss. It's evidence that small, cold bodies can still be complex, structured, evolving, and worth treating as worlds in their own right. So if the old Pluto was a disappointment, it wasn't because Pluto failed to be interesting. It was because our imagination failed to be ambitious enough. And that's the quiet gift of New Horizons. It reminds us that the solar system still has places where our assumptions go to die, and wonder takes their place. If you want a continuation, tell me, should the next video explain, simply, how New Horizons measured the composition of Pluto's ices and atmosphere?